Continuing with section 6, we have the second half of the section to go. We are now analyzing the sketch of f of x equals x over the square root of x squared plus 2. So the first thing we need to do are find any zeros. That occurs at 0, 0. Any vertical asymptotes, and there aren't any. Horizontal asymptotes, and that occurs at plus or minus 1. So it's actually at both negative and positive 1. We can tell from the exponents, because the square root is why we have plus or minus. And then we need to take the derivative. Again, skipping that math part so we can get straight into the new calculus part of the section. So critical values, none, based on our first derivative. And the second derivative is negative 6x over x squared plus 2 to the 5 halves. And we have a possible point of inflection at 0. Okay, so we're going to make a table based on that. So the only point we really need to test is 0. So this is kind of an easy chart. Intercepts negative infinity to 0 and 0 to infinity. You're still testing it in the first derivative and the second derivative to get our conclusion. From negative infinity to 0, our first derivative is positive, and then it is also positive on the second interval. And the second derivative is positive and negative. So our conclusion is that we are increasing concave up and increasing concave down. So before we sketch, we know that there's not going to be any extrema, but we do have a POI at 0, 0 at our x-intercept. Okay, so now to the left we're going to do a rough sketch. Only thing that we know, 0, 0. And horizontal asymptotes at 1 and negative 1. Okay, so sketching, we know that we are going to be increasing and concave up from negative infinity up until that first 0. And then after the 0 we are decreasing, still increasing, but we're concave down. The concavity had changed at that point, so that is a rough sketch of that function. Okay, next one. Starting with the intercepts as always. 0, 0, and 25 over 8, 0. 125 over 8 is 15.6 or so. This is 15.625. Just for reference. And we don't have any asymptotes. None. None. So we're going to go straight into the derivative. So from the derivative, our possible critical points are at 0 and 8. And then our second derivative is 20 times x to the 1/3 minus 1 over 9 x to the 2/3. And our possible points of inflection from there are at 0 and 1. So our chart, we need to test 0, 1, and 8 in our intervals. Negative infinity to 0, 0 to 1. So that should be an 8, not infinity. 1 to 8 and 8 to infinity. So we need to test that in the first derivative, in the second derivative, and then come to our conclusion on the bottom. Negative infinity to 0, our first derivative is positive. 0 to 1, it is negative. 1 to 8, it is negative, and 8 to infinity, it is positive. Second derivative, negative, negative, positive, positive. So our conclusion is that we are increasing while concave down, decreasing while concave down, decreasing while concave up, and then increasing while concave up. So it looks like we do have some extrema to talk about before we can sketch. We're going to have a max at 0, and we plug that back in, we get 0. And we're going to have a min at 8. And the y value that goes with our min is negative 16. And we also have a point of inflection. Point of inflection at 1. At 1, negative 3. So I actually need to erase these over here so that we can actually sketch in our graph. And remember, we have to go down to negative 16. I'm going to go by 2's. 4, 6, 8, 10, 12, 14, 16. Might as well go by 2's on the x-axis as well. Alright, so our points that we need to worry about. We had an x-intercept at 0, 0. And we also had one at 15. Actually, we don't think we went out far enough. 2, 4, 6, 8, 10, 12, 14, 15. So our other x-intercept is out here. And we know we had extrema at 0, 0, so we have that one, and a minimum at 8, negative 16. 2, 4, 6, 8, and then all the way down here. Okay, up until 0, we are increasing and concave down. Okay, we're going to still be concave down, down to our 1, and that's where our point of inflection occurs. Our point of inflection is at 1, negative 3, which is about here. So concave down, and then our concavity changes to concave up until our minimum at 8, negative 16. So notice how we're concave down here. We're going to kind of change shape to make it concave up. And then from 8, negative 16 to infinity, we are increasing concave up. We have to make sure we go through our other 0. Okay. So next one, we need to do the x-intercepts. Those occur at 0 and 4. And no asymptotes at all. Do the first derivative. I'm going to factor it out. Leave it in factored form, I mean, so we can find the critical points easier algebraically. 1 and 4. And then we also need to take the second derivative. Notice that when we do it this way, it helps us find our possible inflection points and our critical points better when we use it in factored form versus leaving it as a polynomial. We'd almost have to graph it to find the zeros. So possible points of inflection occur at 2 and 4. So let's go ahead and make our intervals. test from negative infinity to 1, since that's our first critical point. 1 to 2, 2 to 4, and 4 to infinity, testing our first derivative, second derivative, and coming to a conclusion. Negative infinity to 1, our first derivative is negative, then positive, positive, positive. Second derivative is positive, positive, negative, positive. Conclusion is decreasing, concave up, increasing, concave up, increasing, concave down, and increasing, concave up. Okay, so we have extrema at 1. One negative 27, and we have points of inflection. 2 of them, one at 2, one at 4. Let's find those y values. Okay, so I paused to put in those y values. Our points of inflection are at 2, negative 16, and 4, 0. So now we need to do a rough sketch of this. Putting in our x-intercepts, one of them occurs at 0, one of them occurs at 4. I'm going to go by 4s in the y direction. Just so we can get to one of our extrema there. So 1, negative 27. Point of inflection at 2, negative 16. Okay. So from negative infinity to 1, we are decreasing and concave up. Very sharp, so it was a little rough, but then we are increasing from 1 to 2 and concave up. At 2, we kind of change direction, concave down, and then from 4 to infinity, we are increasing and concave up. Point of inflection at 4, 0 changes shape too. So that was a pretty rough sketch, but that's a pretty good guess at what we were working on. Okay, last one. Our x-intercepts. Only one, we have pi over 2. We don't have any, oops, we have vertical asymptotes at negative pi over 2 and 3 pi over 2. No horizontal. Okay, f prime. Negative 1 over 1 plus sine x. So our critical points actually don't have any. And the double derivative is cosine x over 1 plus sine x squared. Our possible points of inflection are also none. So we are only testing from negative infinity, negative pi over 2 to 3 pi over 2 because we have asymptotes. So we'll make our table. We're not starting at negative infinity. We're going to start at negative pi over 2. Our interval is first going to go to pi over 2 because that's an x-intercept. We kind of want to know what's going on there. From pi over 2 to 3 pi over 2. We're putting it in the first derivative, second derivative, and then coming to our conclusion on the bottom. What is going on? We are negative and negative on the first derivative, and positive, negative. Oops, we should be concave down there. I'm just crazy today. Decreasing, concave down, increasing. I'm sorry. Let's do this one more time. First derivative, decreasing, decreasing, increasing, decreasing. That is better. So decreasing, concave up. And then decreasing, concave down. So we are decreasing on the entire domain. Let's try to make a sketch of this. There's our first vertical asymptote at negative pi over 2, and the second one at 3 pi over 2. We have a 0 at pi over 2. And that is roughly what our function should look like. Okay, that was sketching curves, section 6.